Okay, so these last notes are called searching notes. It's kind of similar to sorting. And I mentioned Thursday you're going to have your open notes tests. And just so you can start gathering different notes together so you have them all close by. The things you want to start looking for are anything to do with matrices. String methods, which we'll review a little bit probably tomorrow. That was that we did with Magpie. It's a while ago. We never had a test on it. It's like index of and substring and stuff like that. And then this is today's stuff, searching. All right, so similar to all the different sorting algorithms, there's lots of different searching algorithms. And searching algorithms are what you would use if you're going through an array looking for a specific value. So I'm going to do two of them, just like we did for sorting. First one's probably how you would write it if you were to come up with a method for this. It's called linear search. And linear search, you are looking for an element in an array. So I'm just going to write it out. We'll talk about it, and it should make sense to you, I think. So I'm going to say where it is, position, so it's going to be a public int. Public int linear search. And you would need to have an array, so int bracket bracket a, and the value to search for, I'll just call it int value. And our precondition is an integer array and a value to search for. And the post condition returns the position of the value. I'm not writing it, but really I should say it's the position of the first occurrence of the value, if it's in there multiple times, or -1 if it's not in the array. All right, so if you had an array and you were looking for a specific value, how would you think to do it? For loop. So this is just not a matrix, it's just an array. So for int I equals 0, I is less than a dot length, I plus plus. Okay, then what would go inside the for loop? If statement. If what? If what equals value? Good. If a bracket I equals value. So if I find the value, what should I do? Return I. Good, because I want the position. I don't want to return the value because I know what the value is. And that's pretty much it. And then outside the for loop, I'm going to write what? I think so. Return -1, right? Because if it gets all the way through and never finds the value, we return -1. That's linear search. All right, so like I said, I thought linear search would make sense. The easiest way to search for a value. not necessarily the most efficient. What was our measure of efficiency for all these different algorithms? What do we use? Big O notation. And we're not even going to have to do too much work to figure out what the big O notation would be here. The worst case scenario for n elements, how many comparisons would I have to make? If I had 10 elements, I'd have to look at 10. It's at the last spot. So the Go notation would be for n elements. Linear search is big O of n. All right, so what we want to do is we want to look for a more efficient method than linear search. And again, there's different algorithms that can do this, but one thing that cuts down the amount of work that you have to do is binary search. So this is a more efficient method. Well, binary search. In the end, we're going to talk efficiency with binary search also. So how I like to keep them straight in my head, O of n is like n to the first power, that's linear. So it's not growing super fast, but it's growing at a constant rate. So for the more elements I have, the longer it's going to take to figure it out at a pretty constant rate. It's linear. We'll see what type of function it becomes for binary search. Binary search does have a precondition. And the precondition with binary search is that it only works if the array is sorted low to high. The array must be sorted low to high. And the algorithm, if I had to summarize what it does, it checks the middle value. Then searches left or right. So basically, if it's already sorted and I'm looking for a particular number, I can find the middle value in the array, look at that number, see if that's bigger than the number I'm looking for or less than the number I'm looking for. Since it's already sorted, I only have to look to the left of it or only have to look to the right of it if it's not the number I'm looking for. So before we actually write the code out, we'll kind of show you what's going on with it. Make the code make more sense. So let's say I've got this array. I've got 1, 2, 3, 4, 5, 6 elements. And it's sorted. So obviously this would be the lowest number. This would be the highest number. If I'm counting in looking for the middle, there's kind of two middle values, so we'd have to pick one. So we'll say this is the middle. Start out with. What I just said a second ago, I'm looking for a particular number. I'm going to compare that to the middle value in the array. If my number's bigger than that, I only need to look to the right. If my number's less than that, I only need to look to the left. I'm going to keep doing that until I find my number, or until I find something happens that makes me know that my number's not in the array. Okay, so let's do a specific example with numbers so you can see what's going on. Here's my array A. My array. I'm going to make it 0 through 5. And I'm just going to put some random values in here. We'll say this is 1, 3, 4, 5, 9, 11. It's important that I keep track of what's the low spot, what's the high spot, and what's the middle spot, because that's how my code is going to work. So let's say we are looking for value equal to 2. I want to find 2. Obviously, I can look at this array really quickly, and I know 2's not in it, but we got to give the computer some steps to make it figure out the 2's not in there. Okay, so to start out with, index 0 is obviously the low number. Index 5 is the high number. I need to know some way to find the middle. So to find the middle, I'm just going to do low plus high divided by 2. And I'm talking about index because I want to know the middle spot. So if I'm saying the low spot's 0, the high spot's 5 divided by 2, what would 5 divided by 2 equal? 2. So it's going to pick 2 for my middle spot. So it's not really a true middle. 2 and 3 are kind of both in the middle. Okay, so just to keep track here, the first time through, low is spot 0, high is spot 5, middle is spot 2. And I'm going to check a couple things every time. First, I'm going to check, is the value equal to a bracket, whatever the middle spot is? So I'm saying, is my value 2, is that equal to what's stored in space 2? 4. Obviously not. And furthermore, the value I'm looking for is actually less than that spot that was in the middle. So there's no reason for me to look at any of these spots if it's sorted, because if the value I'm looking at is bigger, then that means my value must be somewhere to the left. Okay, so what's going to happen is I'm going to immediately change my highest spot. The highest index I need to look at now is spot 1. So I know 2 wasn't right, and my number was lower. So now high is 1, low hasn't changed, low is still 0. If I wanted to find the new middle spot, low plus high divided by 2, 0 plus 1 is 1, 1 divided by 2 end up being 0. So this is the low and the middle spot of what's left, because I'm only looking here. And I check again, is value equal to a bracket, whatever I'm saying the middle is? My value is still 2. What's stored in the spot I'm calling the middle is 1. So obviously value is not equal to that. And this time the value I was looking for is bigger than the middle spot. So that means it can't be to the left of the middle spot, it's got to be to the right of the middle spot. So I can have a new low value now. I would immediately make low, since 0 was too low, spot 1 would have to be my low now. High wouldn't change, high is still 1. If I'm saying low is 1 and high is 1, what would middle end up being? 1 plus 1 divided by 2? Still 1. So at this point, everything is all resting on spot 1. I haven't checked spot 1. As far as the computer knows, it might be a 2. It has potential to be a 2. So I check, is value equal to whatever that middle spot is? Okay, well this time value still 2. But the thing stored in the middle spot is 3. Obviously they're not equal, so it hasn't found the number I'm looking for. And this time, my value is less than that middle spot. So if I keep with that same pattern of what I've been doing, since I'm less than that middle spot, the computer would think, well, then you must be to the left of that. So now it would say high is 0, low is 1. Why does that not really make sense? How could the high spot be 0 and the low spot be spot 1? It's not in order anymore. It's not going from low to high. So here we've got an error. So that means value is not in the array. So I only had to check 3 times before I could figure out that something happened and my value isn't actually in there, as opposed to having going through every single spot and checking. So it's always going to work. It always is, but it is a little trickier than linear search. Any questions yet? Okay. So I want to write out the code for this scenario that we just did. This is public int binary search. Just like before, I need an array. I need a value to search for. Precondition is a sorted int array. So remember, it has to be sorted now. Sorted int array and value search for. Post condition, same as the other post condition. Returns position of value, or -1 if not an array. And I've got my example to refer back to, but I need to be able to write this in general. So I'm going to need to keep track of where my low is, where my high is, where my middle is. So I'm definitely going to need variables for that. I'm going to start with int low. And no matter how big my array is, what's always going to be the initial low spot? 0. How can I write what my high spot would be? In this last example, it was 5 to begin with, but in general, how could I get to that spot? A.length has to be -1, though, right? So the last position would be A.length -1. And then mid, I'm just going to leave as int mid for now, because I'm going to need to calculate that every single time. So the first thing I need to do is, once I know my low and high, I'm going to have to calculate what my mid is. I don't necessarily know how many times I'm doing this. I'm not using a for loop here. I'm just doing it until I can figure out the value's not in the array. So for loop isn't the best type of loop to use here. While would be more appropriate. So while something, and we'll fill in that something at the end, thinking about what that could be. The first thing I need to do is I need to figure out where is that middle spot. And I was trying to show you the calculation I was doing for the middle spot every time. How am I going to find which spot is going to be my middle? Good. Low plus high divided by 2. And that'll do integer division, so if it's not a nice spot, we'll get where we need to be. So I know we did an example. Let me just do another one off to the side in case we need it while we're doing it. Initially, this is low, this is high. This would be middle. Okay, so every time, the first thing I did is I compared value to what this middle spot was. So if a bracket mid is equal to the value I'm looking for, then that's great news because we found what we need to do, and I can just say return what would be the position of value? Mid. But if it's not the value I'm looking for, it's got to be either higher than the value I'm looking for or the lower than the value I'm looking for. So I would do else if. Let's do if a bracket mid is less than the value I'm looking for. So just figure out what to do. Let's say a bracket mid is 5 and the value I'm looking for is 10. So if I look at the middle spot and it's 5 and I'm looking for 10, where must 10 be in the array? Would it be to the right of that or to the left of that? Obviously 10 would have to be somewhere in the right over here. So what would have to change? What I'm calling low or what I'm calling high? Low, right? High is still this last spot, but the lowest spot now in my example would be spot 3. What do you think I'd set it equal to in here to do it in general? Mid plus 1. Good. High doesn't need to change. High could still be the high spot here. Now I'm only searching in here, and it's going to calculate my new middle the next time this while loop runs. Okay, so the only other case, I'm just going to use it as else, but if it's a bracket mid is greater than the value I'm looking for. So if I use my same example over here, that middle value, let's say that my original middle value here was 5. Let's say I was looking for a number like 4. If middle was 5 and I was looking for 4, then I must be somewhere over here. So what am I going to need to change? High. I'm going to set high equal to mid minus 1. And that's going to go back, calculate a new middle, and see if it finds it again. Now we know if it never finds it outside this while loop, we're going to have to return -1, just like in the last method. Any idea? Anyone have any idea what's going to go inside this while loop? How do I know I haven't found the number and I'm never going to find the number because it's not in there? About this last example, what happened? Good. While high is greater than low. And we actually have to say while high is, since they can all be equal, to still check that last spot. We have to say while high is greater than or equal to low. Do all of that. Any questions with that? Okay. Let's do one more example of a type of test question you could see now with binary search. So obviously you don't have to memorize this code because you can use it on the test. Here's another binary search test type question. Here's A again. And I'm going to make it the same size, so index 0 through 5. And we'll put 1, 3, 4, 5, 9, 11. And the first question I'm going to ask, let's say we're looking for value equals 10. What is the search interval? Means what's low and what's high. After the first pass through the while. Basically, it wants to know, follow through that code one time, look at what low is, look at what high is at the end of that first time through. That'd be the answer. All right, so if you go back to that code, we know before the while loop even starts, we set low equal to 0, high equal to a dot length minus 1. So before I even start, low is 0, high is a dot length minus 1, which would be 5 in this case. And then here's the first pass through the while loop. First thing that happens is I find the mid spot. And the while loop goes low plus high divided by 2, which is 5 over 2. So we get 2. Here's low, high, mid. And then the while loop checks if a bracket 2 is equal to the value of 10. A bracket 2 is 4, so 4 is less than 10. If I go check my code real quick again, if a bracket mid is less than 10, right here, a bracket mid is less than 10, low changes, low becomes mid plus 1. So that means low would become what's mid plus 1 right now. So 2 plus 1 would be low is 3. High stayed at 5. So after my first pass through the while loop, the answer would be, we search from A3 to A5. That's the search interval after the first pass through. Question for that question? Okay. Alternate question I could ask. How many passes through the while loop? To determine that 10 is not in the list. This one's the same type of thing I was doing this last one, except I can't stop after one time through. I got to keep going until that while loop happens. And that while loop's going to stop as soon as low and high crisscross over each other. So some of the work for this second question we've already done. We know that before I even start, low is 0, high is 5. And we know that the first pass through, mid was 2, and we switched low to being 3 and high to being 5. As long as this value right here is less than this value right here, the while loop's going to run another time. Less than or equal to, I should say. So the next time through, mid's going to become 3 plus 5 divided by 2. And if you think about it, that should make sense. What's the mid of 3 and 5? Obviously 4. So there's mid now up here. So mid is 4. I'm going to look and see is what's in spot 4. 9 is still less than 10. So since 9 is less than the number I'm looking for, what's going to change, low or high? The number I'm looking at is less than the number I need. Do I look to the right of it or to the left of it? I look to the right. So is low going to change or is high going to change? Low. What's low going to become? 5. I stays at 5. Does the while loop still run if I've got 5 and 5 here? Still okay. So we're going to go a third time. Okay, so now low and high are both 5. So obviously what's mid going to be? Also 5, that same spot. So everything's that same spot. In the middle spot is 11. 11 is greater than 10, the number I'm looking for. So anytime I find a number bigger than what I'm looking for, it means I got to search to the left of it. So what's going to change, low or high? High. So low stays at 5, but high is going to become 1 less than mid. High is going to go down to 4. Now this is the high. Is that going to make the while loop still run? No, because low and high crisscrossed. There's my error. So we return -1. And my answer, how many passes through the while loop? 3 passes. Okay, so that is the type of question you could see involving binary search. Do some practice with it tomorrow. Last thing for today, we got to talk about that big O notation. Said binary search is more efficient. How much more efficient is it? For n elements, binary search is big O of, fill that in at the end. This one's a little trickier than linear search. Essentially what you're doing is you're cutting the array in half every time. You're only looking to the right of a certain spot or to the left of a certain spot. So cutting array in half each time. So let's start with an easy number, like 1,000. If I've got 1,000 elements, and I'm always thinking worst case scenario, so I'm thinking that I don't find the number and I have to return -1 at the end. The first time through, I'm either going to look to the left of 1,000 or the right of 1,000. So after the first time through, there's about 500 elements I'm looking at. After the next time through, there's about 250 elements I'm looking at. And then 125, I keep cutting it in half. Half of 125 is 62.5, so we'll just say 62. Half of that's 31. Half of that's 15.5, so about 15. Half of that's 7.5, so about 7. Half of that's 3.5, so 3. That's 1.5, so 1. You count up how many times I had to half it, which is the number of comparisons I'm making. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 times. So essentially, and it doesn't really matter if you know where I'm coming up with this equation or not, but I'm going to tell you, I'm cutting it in half every time. I want to know how many times I could double a number and still be up to 1,000. So 2 to what power equals the number of elements I have is what I'm really solving. That's how many times I've got, how many halves I've got. Everyone who's in trig now should know this. If I wanted to solve for x in this equation, I need to get rid of that 2. What should I do to both sides of the equation? Log, exactly. If you log both sides, you eventually get that x should be log base 2 of n, but log is what we care about. So that means the binary search has big O of log n efficiency. And log n, those graphs look something like this, which in the long run grows a lot slower than a linear graph, which was what binary search was. So for this case, Django notation tells us the binary search is way more efficient than linear searches. It's a lot less comparisons, a lot less work for the computer. All right, so that's the last of the new notes. Tomorrow, I've got a searching and string method practice questions we're going to do together. I'll review quick about string methods like substring, index of. That's going to be on the test, and we'll go from there.